Hello. Okay. Today I'm going to continue to study the tinygrad project on GeoHots. I'm just going to study this onnx. The interesting thing about this is that I might be able to use this or something similar to help me do the stuff that I'm trying to do. Because as far as I understand now, this stuff takes a machine learning model from one framework and translates to other frameworks. That's the point of the library. And the way that the unit test works is when you put the pytest as the command line argument here, it searches for all the files that have this test here. But if you pass a specific file, it's just going to run the tests that from that file that have the inherit unit test class. And in this file here, it runs this command here based on this stuff here on the globals. So it runs this function, which I think is a Python function, and then calls this update, or maybe it's from onnx. And then based on this class that it creates there, it runs a bunch of tests. So I think right now I'm going to try to understand how that works. And I think tomorrow I'm probably gonna go back to doing the React stuff, so I don't get too sidetracked. Not sure how to say that in English. And I've watched a little bit of his stream yesterday, and he explains why he's doing this. And I think that I sort of agree with him, but not 100%. And I think it makes sense that the stuff that he says, that right now the state of the things, the way that the things are, is that only a few companies are going to have control over all the computing because they have all the GPU power, and then everyone's going to make API calls to OpenAI and all this and these other companies, and they are going to have all the control of the AI. And then this leads to an authoritarian future. And then his goal with this stuff is to give more power to more people, so that other people can also have control of the computing power. But so it's pretty much like the same. He made the analogy, I think, with the gun control, that like if the government has a monopoly on guns, then they control everything, so it's better to give everyone their own guns, so that way that the government can't control everyone. But I think the problem with that argument is that is obviously a gradient, and I think George understands this, but like this is the reason why I think that we need to create a consensus protocol system from the blockchain that, and this is the challenge, because the protocol system has to take into account the hardware, so it has to be integrated in the infrastructure of the economics, of macroeconomics, and that's the challenge, I think. But pretty much the way that I look at it is that these things are related to the distribution of power, because if everyone has their own gun, it's not that problematic, but in the United States, the way that it is right now, there's accidents all the time and terrorist attacks, and not terrorist attacks, but when people shoot up colleges and things like that, that a bunch of people die, and this happens all the time. And the reason why is because everyone has access to guns easily. So what you're making is increasing the probability that you're gonna have catastrophic events because everyone has more power, and because the probabilistic nature of the way that the social structures work, you're always gonna have a percentage of the population that is gonna do things like that because it's part of the genetics. So it's kind of like Hitler. Like natural tendency of people is to hate Hitler because you put the responsibility outside of yourself, and then you create heroes and villains, and then you don't realize that Hitler is a part of yourself because it's part of your genetics. So it's always going to be part of the distribution of probabilities that make up the social structures. And the thing that happens is that when the environment is structured in a certain way, you're gonna have the situation where you have the Holocaust. So it's not like Hitler is outside of yourself, it's just a probabilistic nature of the way that DNA is shaped based on the environment. And that's a consequence of the distribution of power that any single node of the network has. And if you go either side of the equation, where everyone has too much power, if everyone has access to a nuclear weapon, then we become get extinct because it's too much chaos in the structure. And if only very few people have access to too much power, it becomes authoritarian, which is also a dystopian outcome, but eventually it corrupts itself because it's a fractal pattern, and then like there isn't a single individual that can hold all the power. Even if there is a single individual that holds all the power, it would corrupt itself because the individual is just a collection of systems. So like because of the nature of space-time, you can't have any one of the extremes, otherwise space-time would be different. So the nature of space-time itself is the distribution of these relativistic symmetries that creates the geometrical structure of the current state of things. So I think that the natural flow of the growth of information of the system, of the reduction of entropy, is going to be this wave function from one side of the symmetry to the other, which is going to be this movement from left to right, which is the movement from authoritarian to more decentralized. So like George's tinygrad thing would be like a response to the authoritarian, which would be a movement to the other direction. And the nature of the collective consciousness is this wave function of computation from one side to the other, and that's what creates the evolution of information in the system. So I think that the important thing is not the either or, but is both the frequency of movement from one side to the other, and also the scale of the distribution of power across the nodes and the network that perform the computation. So not so that the amount of power that each node has is directly or inversely correlated with the amounts that they can shape the whole structure, so that it doesn't get out of balance with the exponential increase in power. So I think the only way to do that is to programmatically create something that allows us to create a consensus protocol that's gonna create a network of computing that's not gonna be self-destructive as it scales. And the reason why it's going to be adopted is because of the Nash equilibrium of the arms race. So if you make everyone to be incentivized to adopt the blockchain technology because it's going to be more powerful than any single particular agent by themselves, you're going to have a situation where everything is going to be done inside of the network, and then because the network is designed in such a way that there is a correct distribution of power between all the nodes, then it becomes anti-fragile. Obviously the challenge and the fundamental challenge is how you would design the consensus protocol so that regardless of how it scales, it's going to maintain the quote-unquote alignment between the probability of the distribution of the genetics. So yeah. So there's a bunch of different challenges, and that's the issue. It's very hard to think about this stuff. But I think that it makes sense, his goal for tinygrad. Because I also don't like and this is the problem that I see as well, like I see a bunch of people doing these companies where it's pretty much an API call to OpenAI, and then like what are you gonna do if tomorrow they decide to change the way that they are structuring their APIs, like they have all the power, so it's not very good. Actually, I'm gonna write this stuff here. It's calling enable report, which is probably gonna be the thing that creates this stuff here. The thing is about the blockchain is that how do you make it so that, like, and that's the thing that is difficult, because the whole infrastructure of the way that we build things is based on the nature of the economy, which is just exemplification of the patterns of reproduction, which is the natural tendency is going to be for a Pareto distribution because of the way that the physics work. It's just the way that the computation of the collective consciousness evolves in relationship to space-time based on the mass of the probabilities of the genetic mutations that create the structure of society. So over time there's going to be a shift towards a exponential distribution because everything is computed based on the macroeconomics, which is corrupted. So this is the fundamental issue. The problem is not the regulation is bad. The problem is that we are not effective at regulating because the natural tendency of human beings that the collective is to corrupt themselves, and we are not as smart to take into account all the complexity. So that the resulting effect of that is that you have the exponential distribution over time. So this is the problem with creating the challenge with creating the blockchain consensus, because then you are building stuff based on the computing infrastructure, which is the design of which is based on the market economy, which creates this structure where NVIDIA and these big players have control over all the computation. Yeah, I'm sort of familiar with deep learning stuff, but not that much, I think. Hate on. I studied some stuff, but there's obviously a lot more to learn. Like, the thing is, I haven't built anything so far with, except using the libraries, but that's like, it doesn't teach you anything. Like, I used TensorFlow to build some models, and I did the Kaggle courses, but like, it's not the same thing as building the stuff from scratch. So, and also learn that backend is just a name that they give to where you're gonna run the machine learning model, if it's CPU, GPU, and there's other ones that I forgot. I don't understand where this is gonna load the models from if it's not passing only passing the kinds. Yeah, I'm not sure, like, because I have another project going on, and my concern is that I have the tendency of trying to work on too many things at the same time. But like, it got my attention, the bounty stuff from that George posted on Twitter, and also because eventually I wanna, like, in the stuff that I'm doing, I wanna be able to merge it with AI, like. And I have to understand more how AI models work and how to do like this stuff from the ground up, let's say. So I think that the bounties is a great opportunity to learn this kind of stuff. So like, but the thing is, I don't have enough knowledge, I think, and that's the problem. But yeah, so the idea that I had was just to work on this stuff to learn more how it works in practice. So attempt to do a bounty, but realistically, I'm probably not going to be able to do it. And then I go back to working on the stuff that I'm working on, and then maybe I come back to this stuff in the future as well, and I try to connect both things. So I think that a good thing to do would be to because the stuff that I'm trying to do is to create graph networks that represent complex software projects. So I think that eventually what I would like to do is to be able to create graph networks that represent artificial intelligence models. So we can attempt to increase, I don't know how to say that, to make interpretability of models easier, let's say. To be able to try to understand how AI models think, what are the weights that are creating the predictions, and how they are doing that, and how is everything connected. And then, yeah. But mainly, I think in the beginning, I'm gonna try to use this stuff to learn faster. But I think I have to try to merge the two goals together. That's the goal. I think I've looked into this yesterday as well, but I don't understand really well how it works. It says loading the stats based on these paths here. This gets the file, the directory for this file based on data, which is this thing here. And then it probably gets from here, from nodes. So I want to understand how this one, how does this onnx creates the tests? Because I want to be able to understand what is testing here, so that I can figure out if I can fix one of these errors here. But first I need to understand, like, how is it testing this stuff? What files is getting the test from? Is it testing the models here on tinygrad, and which ones are related to each task? Like, understand what is going on here, so I can search for the mistakes and try to fix them. Yo, thank you. I hate them. So it looks like it doesn't do anything in the beginning. It's gonna call this function. You wanna ask ChatGPT what's the .pb extension? No, but maybe it doesn't have. Maybe it doesn't know. A protocol buffer. Yeah, so I think the way that onnx works is serializes the models into these files probably, and then that's what creates the bridge between different frameworks. And I think it does that by creating a graph or something like that. I didn't understand really well the documentation here. I think it creates an abstract syntax tree of the operations, I think. And then it saves them on this format, probably. The question that I'm trying to answer is what? Like, what is the test testing for? I think I'm just gonna study this stuff today and then I'll stop. And then I'll work on the other stuff to finish, to get to the point where it's actually time to create the interpreters or compilers to try to create graphs. And then I go back to this one because I think it's related. Like, it's pretty much the same thing that I'm gonna do, but I'm gonna do it for all of for code and not for. And I think that is gonna be difficult to. I think what I have to do is to create something that, because at some point all of the code, regardless of the language, is gonna be the same. Obviously, when it gets to machine code, it's gonna be the same, but I think you can get to an assembly representation. And there are probably libraries that do that already, so I think I would. Probably the best thing to do is to create something like that, but like, the question would be, is it worth to create like an universal framework that is more like a higher level than assembly, so it is easier to understand? So pretty much like break down code into assembly, then from those assembly pieces create an abstract language that creates like the commonality of all the languages, so that you can create a graph network from that language and then visualize any code in any language based on that abstraction. But then there would obviously be loss of information, I think, because otherwise there wouldn't be any point to having different languages. So, but like, it would allow you to see the essence of everything, let's say, and that's I think what I want to do. But the problem with doing in assembly, translating everything to assembly, is that it's going to be too low level, I think. This is going to be too many redundant things, but maybe it's worth it as well to do that. Like, I also don't have to limit myself. I think I can do both, but it's going to be very hard regardless, I think.
Array 0.40313327, 1.0253217.
And inference is just another way to say testing, as far as I understand. No. So they're talking about inference. They are talking about the ability of the model to predict outcomes, I think.
The onnx standard allows frameworks to export trained models in onnx format and enables inference using any backend that supports the onnx format. onnx runtime is one efficient option. It is available in many platforms. It is optimized for fast inference. Its coverage can be tracked on onnx backend dashboard. onnx implements a Python runtime useful to help understand a model. It is not intended to be used for production, and performance is not a goal. Evaluation of a linear regression hash. Full API is described at onnx.reference. It takes a model proto, a file name. Method run returns the outputs for a given set of inputs specified in a dictionary. Import numpy from import numpy underscore helper. Tensor proto from _helper import. Make underscore model. Make underscore node. Set underscore model underscore props. Make underscore tensor. Make underscore graph. Make underscore tensor underscore value underscore info. From _checker. Import check underscore model from _reference import. Reference. Evaluation of a node hash. The evaluator can also evaluate a simple node to check how an operator behaves on a specific input. Import numpy from import numpy underscore helper. Tensor proto from _helper import. Make underscore node from _reference. Import reference evaluator node equals make underscore node I like. Similar code would also work on graph proto or function proto. Evaluation step by step hash. A converting library takes an existing model train with a machine learning framework, PyTorch, scikit-learn, and converts the model into an onnx graph. Complex models usually do not work on the first try, and seeing intermediate results may help define the part incorrectly converted. Parameter verbose displays information about intermediate results. Import numpy from import numpy underscore helper. Tensor proto from helper import. Make underscore model. Make underscore node. Set underscore model underscore props. Make underscore tensor. Evaluate a custom node hash. Evaluate a custom node hash. The following example still implements a linear regression but adds the identity matrix to A. Import numpy from import numpy underscore helper. What if we combine operators I like and add into A? I like to make it more efficient. We need to evaluate this model as equivalent to the first one. This requires an implementation for this particular node. Predictions are the same. Let's compare the performance on a matrix big enough to see a significant difference. Import time import numpy from _reference. Import reference evaluator from _reference. Op underscore run import. Op run class add I like op run. Op underscore domain equals optimized def underscore run self. X alpha equals 1. Assert length x dot shape equals. It seems worth adding an optimized node in this case. This kind of optimization is usually called fusion. Two consecutive operators are fused into an optimized version of both. Production usually relies on onnx runtime, but since the optimization uses basic matrix operation, it should bring the same performance gain on any other runtime. Implementation details hash. Python and C++ hash. onnx relies on protobooth to define its type. You would assume that a Python object is just a wrapper around a C pointer on the internal structure. Therefore, it should be possible to access internal data from a function receiving a Python object of type model proto. But it is not. According to protobooth 4, changes. This is no longer possible after version 4, and it is safer to assume the only way to get a hold on the content. According to protobooth 4, changes. This is no longer possible after version 4, and it is safer to assume the only way to get a hold on the content is to serialize the model into bytes. Give it the C function, then deserialize it. Functions like check underscore model or shape underscore inference are calling serialize to string then parse from string before checking the model with a C code. Attributes and inputs hash. There is a clear distinction between the two. Inputs are dynamic and may change at every execution. Attributes never changes, and an optimizer can improve the execution graph assuming it never changes. Therefore, it is impossible to turn an input into an attribute, and the operator constant is the only operator changing an attribute into an input. Shape or no shape hash. One usually expects a shape for every input or output assuming the rank, or the number of dimensions, is known. What if we need to create a valid graph for every dimension? This case is still puzzling. Import numpy from import numpy underscore helper. Tensor proto. Function proto from helper import. Make underscore model. Make underscore node. Set underscore model underscore props. Make underscore tensor. Make underscore graph. Make underscore tensor underscore value underscore info. Make underscore obseated. Make underscore function. From checker. Import check underscore model from runtime import inference session def create underscore model shapes. New underscore domain equals custom offset underscore imports equals. Make underscore obseated. 14. Make underscore obseated new underscore domain. 1. Node 1 equals make underscore node map mul. X. A. Saw. Node 2 equals make underscore node add. Saw. A. Y. X equals make underscore tensor underscore value underscore info X. Tensor proto dot float. Shapes X. Equals make underscore tensor underscore value underscore info A. Tensor proto dot float. Shapes A. Y. Equals make underscore tensor underscore value underscore info Y. Tensor proto dot float. Shapes Y. Graph equals. Make underscore graph node 1. Node 2. Example. X. A. Y. Once underscore model equals make underscore model graph. Offset underscore imports equals offset underscore imports. Hash let models runnable by onnx runtime with release your underscore version 1 underscore model dot your underscore version equals 8 return 1 underscore model. Print. Case 1. 2 depth by 2 depth greater than 2D. 1 underscore model equals create underscore model X. None. None. A. None. None. Y. None. None. Check underscore model 1 underscore model. Ses equals inference session 1 underscore model dot serialized to string. Providers equals CPU execution provider. Res equals ses dot run none. X. Numpy dot random dot ram 2. 2. A type numpy dot float 32. A. Numpy dot random dot ram 2. 2. A type numpy dot float 32. Print res print. Case 2. 2 depth by 1 depth greater than 1D. 1 underscore model equals create underscore model X. None. None. A. None. Y. None. Check underscore model 1 underscore model. Ses equals inference session 1 underscore model dot serialized to string. Providers equals CPU execution provider. Res equals ses dot run none. X. Numpy dot random dot ram 2. 2. A type numpy dot float 32. A. Numpy dot random dot ram 2. A type numpy dot float 32. Print res print.
I think the stuff that this is doing is pretty much similar to the thing I was talking about. So it just creates it serializes code into these graphs, which is this language probably similar to an abstract syntax tree that allows you to move around between different frameworks. I think it's similar, but it's not exactly the same as the stuff that I am trying to do. So it probably runs all the stats on when you run the function there. I think that I don't remember where I saw, but I think that this also represents where what thing is running. I think like this is the class, and then maybe the function here, but I'm not really sure. Backend. I think if I run on other file, the command on other file I'm gonna be able to. No, but I think this is the file, and then this is the class, and then the function. But obviously this file is not the one that contains the function because it's inheriting. And I think that he's not testing the models because it takes too long now. So just testing for this stuff here. And then inheriting the backend class for this. So it's doing this backend task. So obviously he's getting the tasks from this stuff. So it's load the tasks here and then adds the tasks here and then runs them probably instead of the, or loads and then runs instead of this function. And the neighbor report is the function that is calling there. So maybe it adds everything and then on this function is the one that calls, that runs the tasks. I'm not really sure. Yeah, so the task function is the run function. Which is gonna be this function here. So these tasks are the ones here instead of the data, right? The thing is, I can't look into the files. Not sure if the documentation has. I'm gonna ask ChatGPT probably.
Changes made on May 6, 2022. Changes made to protocol buffers on May 6, 2022. Versioning. We changed our versioning scheme to enable more nimble updates for language-specific parts of protocol buffers. In the new scheme, each language has its own major version and can be implemented independently of other languages, as covered later in this topic with the Python release. The minor and patch versions, however, will remain coupled. This allows us to introduce breaking changes into some languages without requiring a bump of a major version in languages that do not experience a breaking change. The first instance of this new versioning scheme is the new version of the Python API, 4.21.0, which follows the preceding version, 3.20.1. Other language APIs will be released as 3.21.0. Python updates. We made some changes in Python language supporting protocol buffers. Version 4.21.0 is a new major version, following 3.20.1. The new version is based on the UP library and offers significantly better parsing performance than previous releases, especially for large payloads. It also includes pre-built binary modules for Apple Silicon for increased performance without a manual build. The new release does contain some breaking changes. Specifically, the unknown fields method, which relied on an implicitly created class, is replaced with the explicitly created unknown field set class. Some non-core characteristics may have changed, such as the specific format of certain strings or error messages. These are not considered breaking changes, but may still impact your existing code base. Applications that rely on sharing messages between Python and C++ break in the new version. Most developers won't be affected by this, but users of Nucleus and possibly other libraries may be. As a workaround, you can set an environment variable that forces the library to preserve compatibility. Python up requires generated code that has been generated from Proto 3.19.0 or newer. JavaScript support. We moved some things around for protocol buffer support JavaScript to allow JavaScript to evolve and release independently of the main repo. Specifically, we decoupled the language support from the main project and moved it into its own repository. If you have created any pull requests related to JavaScript supported protocol buffers that you still like to merge, feel free to replicate those against the JavaScript repository. Proto's hash. This structures are defined in protobuf in files 1/proto. It is recommended to use function in module 1.helper to create them instead of directly instantiate them. Every structure can be printed with function print and is rendered as a JSON string. Attribute protohash. This class is used to define an attribute of an operator defined itself by a node proto. It is a named attribute containing either singular float, integer, string, graph, and tensor values, or repeated float, integer, string, graph, and tensor values. An attribute proto must contain the name field and only one of the following content fields, effectively enforcing a C++ union equivalent. Class 1.attribute protohash. Descriptor equals google.protobuf.pyx._message.message descriptor object hash. The google.protobuf.de descriptor.descriptor. For this message type, doc underscore function protohash. This defines a function. It is not a model but can be used to define custom operators used in a model. Class 1.function protohash. Descriptor equals google.protobuf.pyx._message.message descriptor object hash. The google.protobuf.de descriptor.descriptor. For this message type, attribute hash. Field 1.function proto.attribute. Attribute underscore protohash. Field 1.function proto.attribute underscore proto. Doc underscore string hash. Field 1.function proto.doc underscore string. Domain hash. Field 1.function proto.domain. Input hash. Field 1.function proto.input. Name hash. Field 1.function proto.name. Node hash. Field 1.function proto.node. Offset underscore import hash. Field 1.function proto.offset underscore. This defines an operator. A model is a combination of mathematical functions, each of them represented as an once operator, stored in a node proto. Computation graphs are made up of a DAG of nodes, which represent what is commonly called a layer or pipeline stage in machine learning frameworks. For example, it can be a node of type that takes in an image, a filter tensor and a bias tensor, and produces the convolved output. Class 1.node protohash. Descriptor equals google.protobuf. Operator protohash. This class is rarely used by users. An operator proto represents the immutable specification of the signature and semantics of an operator. Operators are declared as part of an operator set, which also defines the domain name for the set. Operators are uniquely identified by a three-part identifier: domain, op underscore type, since underscore version, where domain is the domain of an operator set that contains this operator specification. Op underscore type is the name of the operator as referenced by a node proto.op underscore type. Since underscore version is the version of the operator set that this operator was initially declared in. Class 1.operator protohash. Descriptor equals google.protobuf.pyx._message.message descriptor object hash. The google.protobuf.de descriptor.descriptor. For this message type, doc underscore string hash. Field 1.operator proto.doc underscore string. Op underscore type hash. Field 1.operator proto.op underscore type. Since underscore version hash. Field 1.operator proto.since underscore version. Status hash. Field 1.operator proto.status. Operator set proto hash. This is the type of attribute offset underscore import of class model proto. This attribute specifies the versions of operators used in the model. Every operator or node belongs to a domain. All operators for the same domain share the same version. Class 1.operator set proto hash. Descriptor equals google.protobuf.pyx._message.message descriptor object hash. The google.protobuf.de descriptor.descriptor. For this message type, domain hash. Field 1.operator set proto.domain. Version hash. Field 1.operator set proto.version. Operator set proto hash. An operator set proto represents an immutable set of immutable operator specifications. The domain of the set, operator set proto.domain, is a reverse DNS name that disambiguates operator sets defined by independent entities. The version of the set, opset underscore version, is a monotonically increasing integer that indicates changes to the membership of the operator set. Operator sets are uniquely identified by a two-part identifier: domain, opset underscore version. Like model proto, operator set proto is intended as a top-level file/wire format, and thus has the standard format headers in addition to the operator set information. Class 1.operator set proto hash. Descriptor equals google.protobuf.pyx._message.message descriptor object hash. The google.protobuf.de descriptor.descriptor. For this message type, doc underscore string hash. Field 1.operator set proto.doc underscore string. Domain hash. Field 1.operator set proto.domain. Functions hash. Field 1.operator set proto.functions. Ear underscore build underscore metadata hash. Field 1.operator set proto.ear underscore build underscore metadata. Ear underscore version hash. Field 1.operator set proto.ear underscore version. Ear underscore version underscore pre-release hash. Field 1.operator set proto.ear underscore version underscore pre-release. Magic hash. Field 1.operator set proto.magic. Operator hash. Field 1.operator set proto.operator. Offset underscore version hash. Field 1.operator set proto.offset underscore version. Optional proto hash. Some input or output of a model are optional. This class must be used in this case. An instance of class optional proto may contain or not an instance of type tensor proto, sparse tensor proto, sequence proto, map proto, and optional proto. Class 1.optional proto hash. Descriptor equals google.protobuf.pyx._message.message descriptor object hash. The google.protobuf.de descriptor.descriptor. For this message type, elementary underscore type hash. Field 1.optional proto.elementary underscore type. Map underscore value hash. Field 1.optional proto.map underscore value. Name hash. Field 1.optional proto.name. Optional underscore value hash. Field 1.optional proto.optional underscore value. Sequence underscore value hash. Field 1.optional proto.sequence underscore value. Sparse underscore tensor underscore value hash. Field 1.optional proto.sparse underscore tensor underscore value. Tensor underscore value hash. Field 1.optional proto.tensor underscore value. Sequence proto hash. This defines a dense, ordered collection of elements that are of homogeneous types. Sequences can be made out of tensors, maps, or sequences. If a sequence is made out of tensors, the tensors must have the same element type, i.e. in 32. In some cases, the tensors in a sequence can have different shapes. Whether the tensors can have different shapes or not depends on the type/shape associated with the corresponding value info. For example, sequence tensor float m and greater than means that all tensors have same shape. However, sequence tensor float omitted more than means they can have different shapes. All of rank 2, where omitted means the corresponding dimension has no symbolic/constant value. Finally, sequence tensor float omitted means that the different tensors can have different ranks when the shape itself is omitted from the tensor type. For a more complete description, refer to static tensor shapes. Class 1.sequence proto hash. Descriptor equals google.protobuf.pyx._message.message descriptor object hash. The google.protobuf.de descriptor.descriptor. For this message type, elementary underscore type hash. Field 1.sequence proto.elementary underscore type. Map underscore values hash. Field 1.sequence proto.map underscore values. Name hash. Field 1.sequence proto.name. Optional underscore values hash. Field 1.sequence proto.optional underscore values. Sequence underscore values hash. Field 1.sequence proto.sequence underscore values. Sparse underscore tensor underscore values hash. Field 1.sequence proto.sparse underscore tensor underscore values. Tensor underscore values hash. Field 1.sequence proto.tensor underscore values. Sparse tensor proto hash. This defines a sparse tensor. The sequence of non-default values are encoded as a tensor of shape n and z. The default value is 0 for numeric tensors, an empty string for string tensors. Values must have an empty name present which serves as a name for sparse tensor proto when used in sparse underscore initializer list. Class 1.sparse tensor proto hash. Descriptor equals google.protobuf.pyx._message.message descriptor object hash. The google.protobuf.de descriptor.descriptor. For this message type, dims hash. Field 1.sparse tensor proto.dims. Indices hash. Field 1.sparse tensor proto.indices. Values hash. Field 1.sparse tensor proto.values. String entry proto hash. This is equivalent to a pair of strings. This is used to store metadata in model proto. Class 1.string entry proto hash. Descriptor equals google.protobuf.pyx._message.message descriptor object hash. The google.protobuf.de descriptor.descriptor. For this message type, key hash. Field 1.string entry proto.key. Value hash. Field 1.string string entry proto.value. Tensor proto hash. This defines a tensor. A tensor is fully described with a shape, C shape proto, the element type, C type proto, and the elements themselves. All available types are listed in 1.mapping. Class 1.tensor proto hash. Descriptor equals google.protoboof.pyx._message.message descriptor object hash. The google.protoboof.de scriptor.descriptor. For this message type. Class segment hash. Descriptor equals google.protoboof.pyx._message.message descriptor object hash. The google.protoboof.de scriptor.descriptor. For this message type. Begin hash. Field 1.tensor proto.segment.begin. End hash. Field 1.tensor proto.segment.end. Data underscore location hash. Field 1.tensor proto.data underscore location. Data underscore type hash. Field 1.tensor proto.data underscore type. Dims hash. Field 1.tensor proto.dims. Doc underscore string hash. Field 1.tensor proto.doc underscore string. Double underscore data hash. Field 1.tensor proto.double underscore data. External underscore data hash. Field 1.tensor proto.external underscore data. Float underscore data hash. Field 1.tensor proto.float underscore data. In 32 underscore data hash. Field 1.tensor proto.in32 underscore data. In 64 underscore data hash. Field 1.tensor proto.in64 underscore data. Name hash. Field 1.tensor proto.name. Raw underscore data hash. Field 1.tensor proto.raw underscore data. Segment hash. Field 1.tensor proto.segment. String underscore data hash. Field 1.tensor proto.string underscore data. Win64 underscore data hash. Field 1.tensor proto.win64 underscore data. Tensor shape proto hash. This defines the shape of a tensor or a sparse tensor. It is a list of dimensions. A dimension can be either an integer value or a symbolic variable. A symbolic variable represents an unknown dimension. Class 1.tensor shape proto hash. Descriptor equals google.protoboof.pyx._message.message descriptor object hash. The google.protoboof.de scriptor.descriptor. For this message type. Class dimension hash. Descriptor equals google.protoboof.pyx._message.message descriptor object hash. The google.protoboof.de scriptor.descriptor. For this message type. Denotation hash. Field 1.tensor shape proto.dimension.de notation. Dim underscore param hash. Field 1.tensor shape proto.dimension.dim underscore param. Dim underscore value hash. Field 1.tensor shape proto.dimension.dim underscore value. Dim hash. Field 1.tensor shape proto.dim. Training info proto hash. Training info proto stores information for training a model. In particular, this defines two functionalities: an initialization step and a training algorithm step. Initialization resets the model back to its original state as if no training has been performed. Training algorithm improves the model based on input data. The semantics of the initialization step is that the initializers in model proto.graph and in training info proto.algorithm are first initialized as specified by the initializers in the graph and then updated by the initialization underscore binding in every instance in model proto.training underscore info. The field algorithm defines a computation graph which represents a training algorithm step. After the execution of a training info proto.algorithm, the initializers specified by update underscore binding may be immediately updated. If the targeted training algorithm contains consecutive update steps, such as block coordinate descent methods, the user needs to create a training info proto for each step. Class 1.training info proto hash. Descriptor equals google.protoboof.pyx._message.message descriptor object hash. The google.protoboof.de scriptor.descriptor. For this message type. Algorithm hash. Field 1.training info proto.algorithm. Initialization hash. Field 1.training info proto.initialization. Initialization underscore binding hash. Field 1.training info proto.initialization underscore binding. Update underscore binding hash. Field 1.training info proto.update underscore binding. Type proto hash. This defines a type of a tensor which consists in an element type and a shape. Shape proto. Class 1.type proto hash. Descriptor equals google.protoboof.pyx._message.message descriptor object hash. The google.protoboof.de scriptor.descriptor. For this message type. Class map hash. Descriptor equals google.protoboof.pyx._message.message descriptor object hash. The google.protoboof.de scriptor.descriptor. For this message type. Key underscore type hash. Field 1.type proto.map.key underscore type. Value underscore type hash. Field 1.type proto.map.value underscore type. Class opaque hash. Descriptor equals google.protoboof.pyx._message.message descriptor object hash. The google.protoboof.de scriptor.descriptor. For this message type. Domain hash. Field 1.type proto.opaque.domain. Name hash. Field 1.type proto.opaque.name. Class optional hash. Descriptor equals google.protoboof.pyx._message.message descriptor object hash. The google.protoboof.de scriptor.descriptor. For this message type. Elementary underscore type hash. Field 1.type proto. Serialization hash. Save a model in any protoclass hash. This onnx graph needs to be serialized into one contiguous memory buffer. Method serialized to string is available in every onnx objects. With open model.ones, wb as f.write ones underscore model.serialized to string. This method has the following signature. Class 1.model proto hash. Serialized to string hash. Serializes the message to a string only for initialized messages. Every protoclass implements method serialized to string. Therefore, the following code works with any class described in page protos. With open proto.pd, wb as f.write proto.serialized to string. Next example shows how to save a node proto. From one's import node proto node equals node proto node.name equals example type proto node.op underscore type. Load a model hash. Following function only automates the loading of a class model proto. Next section shows how to restore any other protoclass. 1.loadf. IO bytes. str. Format. Literal protoboof. Text proto. str equals protoboof. Load underscore external underscore data. Bool equals true. Model proto hash. Loads a serialized model proto into memory. Parameters. F can be a file like object as write function or a string containing a file name. Format. The serialization format. Default is protoboof. The encoding is assumed to be UTF-8 when the format is a text format. Load underscore external underscore data. Whether to load the external data. Set to true if the data is under the same directory of the model. If not, users need to call load underscore external underscore data underscore for underscore model with directory to load external data from. Returns. Loaded in memory model proto. From one's import load once underscore model equals load model.ones. Or from one's import load with open model.ones. Air bay as f. Once underscore model equals load f. Next function does the same from a bytes array. 1.backend hash. Backend hash. Class 1.backend.base.backend source hash. Backend is the entity that will take an onnx model with inputs, perform a computation, and then return the output. For one-off execution, users can use run underscore node and run underscore model to obtain results quickly. For repeated execution, users should use prepare, in which the backend is all the preparation work for executing the model repeatedly. For example, loading initializers, and returns a backend ref handle. Class method run underscore node proto, inputs, any, device, str equals CPU, outputs underscore info, sequence tuple dtype, tuple int, none equals none, chords, dict str, any, tuple any, none source hash, simple run one operator and return the results, colon param outputs underscore info, a list of tuples, which contains the element type and param shape of each output. First element of the tuple is the dtype, param and, param the second element is the shape. More use case can be found in param https://github.com/1/main/1/backend/test/main/1/backend/test/main_1 support underscore device str, bool source hash, checks whether the backend is compiled with particular device support. In particular, it's used in the testing suite. Backend rep hash, class 1.backend.base.backend rep source hash. Backend rep is the handle that a backend returns after preparing to execute a model repeatedly. Users will then pass inputs to the run function of backend rep to retrieve the corresponding results. Run inputs, any, chords, any, tuple any, source hash, abstract function, device hash, class 1.backend.base.device str source hash, describes device type and device syntax, device underscore type, device underscore optional example, CPU, CUDA colon 1, device type hash, class 1.backend.base.device type source hash, describes device type, load underscore model underscore test hash, 1.backend.test.loader.load underscore model underscore test data underscore dir, str equals /op/hosted toolcache /python/3.10.11/x64/lib/python 3.10/site package/1.15.0.3.10 linux x86 underscore 64.x/1/backend/test/data kind str none equals none list test case source hash, load model test cases from on disk data files. plus b printf a.numpy plus b.numpy equals result.numpy assert result.numpy 0 equals 5. Welcome to the tinygrad documentation equals this file will take you on a whirlwind journey from a tensor all the way down. Tinygrad has been aggressively refactored in the 2.5 years it's been worked on. What you see here is a refined library with more refining to go still. The whole tinygrad is 2,300 lines, so while it's readable in an evening or two, this documentation will help with entry points and understanding the abstraction stack hash percent hash equals boilerplate imports for typing equals from underscore future underscore import annotations from typing import optional tuple union any dict callable type list class var from a new import a new hash. We will be using the Clang backend from tinygrad.lazy import device.default equals Clang hash first 2 plus 3 as a tensor, the highest level from tinygrad.tensor import tensor equals tensor 2 b equals tensor 3 result equals a plus b printf a.numpy plus b.numpy equals result.numpy assert result.numpy 0 equals 5 hash percent hash equals tensor in tinygrad/tensor.py code 8 tenths equals hash. It's worth reading tinygrad/tensor.py. It's pretty beautiful. Import tinygrad.mlops as mlops hash. This is the good old familiar tensor class tensor hash. These two are pretty straightforward. Grad optional tensor requires underscore grad optional bool hash. This is the graph of the autograd engine underscore ctx optional function hash. This is where the data and other tensor properties actually live. Lazy data lazy buffer hash high level lops are defined on this class. Example relu def relu self return self.maximum 0 hash log is in log. This is the wrapper function in tensor def log self return lops.log.apply self hash. All the definitions of the derivatives are subclasses of function like mlops.log hash. There's only 18 mlops for derivatives for everything in tinygrad/mlops.py code 9 tenths hash. If you read one file read mlops.py. If you read two files also read tinygrad/tensor.py hash. You can differentiate the world using the chain rule class function hash. Example types of forward and backward def forward self x lazy buffer greater than lazy buffer pass def backward self x lazy buffer greater than lazy buffer pass hash percent hash equals lazy buffer in tinygrad/lazy.py code 5 tenths equals from tinygrad.helpers import dtype hash. This is where the properties live that you thought were a part of tensor hash. Lazy buffer is like a tensor without derivatives at the mlop layer class lazy buffer hash. These three define the type of the buffer and they are returned as tensor properties device str shape tuple int dtype hash. A shape tracker is used to track things like reshapes and permutes hash. All movement ops are 0 copy in tinygrad hash. The shape tracker specifies how the data in the raw buffer matches to the shape hash. We'll come back to this later. Shape tracker hash. If a lazy buffer is realized it has a raw buffer hash. We will come back to raw buffers later. Realized optional raw buffer hash. If a lazy buffer is unrealized it has a lazy op hash. This lazy op describes the computation needed to realize this lazy buffer op optional lazy op hash. Lazy op in tinygrad/ops.py code 4 tenths hash. In a tree they form an abstract syntax tree for a single GPU kernel class lazy op hash. The type of the compute src tuple union lazy op lazy buffer hash. The source is arg optional any equals none hash and an optional static argument hash. There's currently 20 ops you have to implement for an accelerator class unary ops enum noop equals auto exp equals auto log equals auto neg equals auto not equals auto class binary ops enum add equals auto sub equals auto mul equals auto div equals auto pow equals auto peak equals auto max equals auto class reduce ops enum sum equals auto max equals auto class movement ops enum reshape equals auto permute equals auto expand equals auto pad equals auto shrink equals auto stride equals auto class load ops enum from CPU. You have to copy the data on the device first. Print lazy op.src0 op assert lazy op.src0 op.op equals load ops from CPU assert lazy op.src0 op.arg.fxn equals 2 the arg of the from CPU lazy op is the 2 assert result.lazydata.realized is none. The lazy buffer is not realized yet hash. Now we realize the lazy buffer result.lazydata.realized assert result.lazydata.realized is not none. The lazy buffer is realized hash. This brings us nicely to device buffer of which the realized Clang buffer is a subclass. Assert raw malloc buffer in str type result.lazydata.realized hash. Getting ahead of ourselves but we can copy the device buffer talkboo assert result.lazydata.realized.talkboo 0 equals 5 when put in numpy with talkboo it's 5 inches hash percent hash equals union interpreted compiled in tinygrad/ops.py code 5 tenths equals hash. Now you have a choice. You can either write an interpreted backend or compile backend hash. Interpreted backends are very simple. Example CPU and torch class interpreted hash. They have a backing raw buffer type raw buffer hash and they have a lookup table to functions for the ops fxn underscore for underscore op dict op callable equals unary ops exp, land x, np.expex, binary ops.add, land x, y, x plus y, hash compiled backend stake. A little more. Example, GPU and LLVM, class compiled, hash they also have a backing raw buffer, type raw buffer, hash a code generator, which compiles the ASD code again, type is kernel, hash and a runtime, which runs the generated code runtime, type runtime, hash runtime is what actually runs the kernels for a compiled backend class runtime ABC, hash name is the name of the function, and PRG is the code hash the constructor compiles the code def underscore init underscore self, name str, PRG str, pass hash call runs the code on the boofs. Note, the output is always boof 0, but this is just a convention def underscore call underscore self, global underscore size optional list int, local underscore size optional list int, boofs list raw buffer, pass hash percent hash equals raw buffer, in tinygrad slash runtime slash lib.py, code 5/10 equals import numpy as np hash raw buffer is where the data is actually held. It's pretty close to just memory class raw buffer ABC, hash create an empty raw buffer that holds size elements of type dtype hash buff is an opaque container class def underscore init underscore self, size int, dtype, buff any, raise not implemented error must be implemented, hash from CPU is class method that creates a raw buffer. It's a class method since some runtimes are 0 copy of class method def from CPU cls raw buffer, xnp.array, dash greater than raw buffer, raise not implemented error must be implemented, hash talkpoo converts the raw buffer to a numpy array with shape, size. Many backends are 0 copy here def talkpoo self, greater than np.array, raise not implemented error must be implemented, hash raw numpy buffer is a raw buffer example for numpy. It's very simple class raw numpy buffer raw buffer. Hash note, the np.array is stored in the opaque container def underscore init underscore self, buff np.array, super, underscore init underscore buff dot size, dtypes.from underscore np buff dot dtype, buff, at class method def from CPU cls, x, return cls x def talkpoo self, return self dot underscore buff hash percent hash equals example. 2 plus 3 and raw clang equals hash raw malloc buffer is the simplest concrete version of raw buffer. In tinygrad slash ops.py, hash it's used for the clang and LLVM backends hash it's just malloc size dtype.item size. From tinygrad.runtime.lib, import raw malloc buffer hash clang program is the simplest runtime. In tinygrad slash runtime slash ops underscore clang.py, code 7/10, hash underscore init underscore calls clang, and underscore call underscore calls the function in the. So outputted by clang hash and clang, global underscore size and local underscore size are ignored from tinygrad.runtime.ops underscore clang import clang program hash. A concrete example looks like this. This adds 2 size 1 raw buffer hash. First we create 2 numpy buffers containing 2 and 3 hash, then we copy the numpy into raw malloc buffers hash last. We create an empty output buffer from tinygrad.helpers import dtypes numpy underscore a, numpy underscore b, equals np.array2, dtype equals np.float32, np.array3, dtype equals np.float32, input underscore a, input underscore b equals raw malloc buffer.from CPU numpy underscore a, raw malloc buffer.from CPU numpy underscore b output, equals raw malloc buffer 1, dtypes.float32, hash compile, the program, run it, and 2 plus 3 does. Indeed equal 5 program equals clang program add, void add float a, float b, float c, equals b plus c, program none, output, input underscore a, input underscore b, hash note, the none are for global underscore size and local underscore size print output.docpoo, assert output.docpoo, 0, equals 5, it's still 5 np.testing.assert underscore roll close output.docpoo, numpy underscore a plus numpy underscore b, hash percent hash equals, as kernel, in tinygrad slash code again slash as.py, code 2/10, equals hash, but we are nowhere near done. Hash we wrote the code above by hand hash we need the lazy op ASTs to be automatically turned into code hash. The current class looks roughly like this, but this will change and we will update the docs hash. This stuff is in the terrible 528 lines of tinygrad slash code again slash code 2/10 aka turd quality, class is kernel, hash create the kernel with the AST hash node. The AST contains the compiled buffers themselves as the root nodes. This will change def underscore init underscore self, as lazy op, pass def code again self, greater than a strunner, pass hash we return a class that runs code on lazy buffers, which are all expected to be realized class is strunner, hash, from tinygrad slash ops.py, def underscore init underscore self, name, PRG, global underscore size optional list int, local underscore size optional list int, pass def build self, runtime, pass def exec self, boofs list lazy buffer, pass hash that hides a lot of complexity that will be refactored, but that's the basic idea of code generation. Hash percent hash equals example. 2 plus 3 auto-generated clang code equals from tinygrad.tensor import tensor result equals tensor, 2 plus tensor, 3, hash we have a global cache used by the G hash from there. We can see the generated clang code from tinygrad.helpers. Import global counters.cache equals, hash enables the cache result.realize hash. Create the program and runs it cache underscore saved equals global counters.cache equals none hash disable the cache hash there's one strunner in the cache assert len cache underscore saved equals 1 PRG, boofs equals cache underscore save 0, hash print the C program smile print PRG.PRG hash after some formatting. The compiler doesn't care. Hash note, the 2 and 3 are constant folded void e underscore 1 float data 0, 4, in ix 0 equals 0, ix 0 less than 1, ix 0 plus, data 0 equals 2.0f plus 3.0f, hash percent hash equals example, shape tracker, in tinygrad slash shape tracker.py, code 7/10, equals hash. Remember how I said you don't have to write the movement ops for compile buffers? Hash that's all thanks to shape tracker. Hash shape tracker tracks the indices into the raw buffer from tinygrad.shape.shapetracker import shape tracker hash create a virtual 10 tensor. This is just a shape. There's no actual tensor. It equals shape tracker 10 hash. You'll see it has one view. The 10 one of the strides. Print a hash shape tracker shape equals 10 views equals view 10 1 0 hash. We can permute it and the strides change a dot permute 1 0. Print a hash shape tracker shape equals 10 views equals view 10 1 0 hash. We can then reshape it and the strides change again. Hash note how the permute stays applied a dot reshape 5 2 5 2. Print a hash shape tracker shape equals 5 2 views equals view 5 2 1 20 10 0 hash. Now if we were to reshape it to a 100 shape tensor, we have to create a second view a dot reshape 100. Print a hash shape tracker shape equals 100 views equals hash view 5 2 1 20 10 0 hash view 100 1 0 hash view stack on top of each other. To allow 0 copy for any number of movement ops hash, we can render a Python expression for the index at any time ix underscore equals a dot x underscore x print ix dot render hash ix 0% 10 plus ix 0 / 10 hash. Of course, if we reshape it back, the indexes get simple again. A dot reshape 10 10 ix underscore equals a dot x underscore x print ix dot render hash ix 1 times 10 plus ix 0 hash. The shape tracker still has 2 views though. Print a hash shape tracker shape equals 10 views equals hash view 5 2 1 20 10 0 hash view 10 1 0 hash until we simplify it. A dot simplify print a hash shape tracker shape equals 10 views equals view 10 1 0 hash. And now we permute it back. A dot permute 1 0 print a hash shape tracker shape equals 10 views equals view 10 1 0 hash. And it's even contiguous. Assert a dot contiguous equals true hash percent hash equals example variable in tinygrad slash shape slash symbolic.py code 6/10 equals hash under the hood. Shape tracker is powered by a small symbolic algebra library from tinygrad.shape.symbolic import variable hash. Variable is the basic class from symbolic hash. It's created with a name and a min and max inclusive. A equals variable a 0 10 b equals variable b 0 10 hash. Some math examples print a 10 min a 10 Max, hash. You'll see a 10 has a minimum of 0 and max of 100 print. A plus B. Min, A plus B. Max, hash, 020. You get the idea hash, but complex expressions are where it gets fun exp equals. A plus B 10. Percent 10 print exp dot render. Hash, A percent 10. Hash as you can see, B is gone. Hash 1 more exp equals. A 40 plus B. // 20 print exp dot render. Hash, a 2. Print exp dot min. Exp dot max. Number 020 hash. This is just a 2. Hash since B only has a range from 0 to 10. It can affect the output hash percent 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29 30 31 32 33 34 35 36 37 38 39 404 14 24 3 4 4 4 5 4 6 4 7 4 8 4 9 5 0 5 1 5 2 5 3 5 4 5 5 5 6 5 7 5 8 5 9 6 0 6 1 6 2 6 3 6 4 6 5 6 6 6 7 6 8 6 9 7 0 7 1 7 2 7 3 7 4 7 5 7 6 7 7 7 8 7 9 8 0 8 1 8 2 8 3 8 4 8 5 8 6 8 7 8 8 8 9 9 0 9 1 9 2 9 3 9 4 9 5 9 6 9 7 9 8 9 9 1 0 0 1 0 1 1 0 2 1 0 3 1 0 4 1 0 5 1 0 6 1 0 7 1 0 8 1 0 9 1 1 0 1 1 1 1 1 2 1 1 3 1 1 4 1 1 5 1 1 6 1 1 7 1 1 8 1 1 9 1 2 0 1 2 1 1 2 2 1 2 3 1 2 4 1 2 5 1 2 6 1 2 7 1 2 8 1 2 9 1 3 0 1 3 1 1 3 2 1 3 3 1 3 4 1 3 5 1 3 6 1 3 7 1 3 8 1 3 9 1 4 0 1 4 1 1 4 2 1 4 3 1 4 4 1 4 5 1 4 6 1 4 7 1 4 8 1 4 9 1 5 0 1 5 1 1 5 2 1 5 3 1 5 4 1 5 5 1 5 6 1 5 7 1 5 8 1 5 9 1 6 0 1 6 1 1 6 2 1 6 3 1 6 4 1 6 5 1 6 6 1 6 7 1 6 8 1 6 9 1 7 0 1 7 1 1 7 2 1 7 3 1 7 4 1 7 5 1 7 6 1 7 7 1 7 8 1 7 9 1 8 0 1 8 1 1 8 2 1 8 3 1 8 4 1 8 5 1 8 6 1 8 7 1 8 8 1 8 9 1 9 0 1 9 1 1 9 2 1 9 3 1 9 4 1 9 5 1 9 6 1 9 7 1 9 8 1 9 9 2 0 0 2 0 1 2 0 2 2 0 3 2 0 4 2 0 5 2 0 6 2 0 7 2 0 8 2 0 9 2 1 0 2 1 1 2 1 2 2 1 3 2 1 4 2 1 5 billion 216 million 217,218. In the context of tensors in machine learning, the term stride refers to the step size or the number of elements to skip while traversing a tensor during various operations like convolution or pooling. When performing operations such as convolution or pooling on a tensor, a small window or kernel moves across the tensor to compute the output. The stride determines how this window moves. A stride value of 1 means the window moves 1 element at a time, while a stride value of 2 means the window skips 1 element and moves 2 steps at a time. Using a larger stride value can reduce the output size and computation cost, as it skips elements and performs computations on a smaller number of locations in the input tensor. However, it also leads to a loss of information and spatial resolution in the output. Here's an example to illustrate the concept of stride in a 2D tensor. Mark down copy code input tensor. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 22 by 2 convolution with stride equals 2. Window 1, 1 2 window 2, 3 4 6 7 8 9 output. 1 2 3 4 6 7 8 9. In the example above, we have a 2 by 2 convolution operation with a stride of 2. The window moves 2 steps horizontally and vertically to compute the output. As a result, the output tensor has a reduced spatial size compared to the input tensor. By adjusting the stride, you can control the degree of downsampling or compression in the output tensor, which can be useful for tasks like feature extraction or dimensionality reduction in machine learning models. Free research.
I think I remember studying this stuff on the, or seeing this stuff on the brilliant.org course about neural networks. Now I remember. It's just the step of the window, but I don't remember really well how it works. Pretty sure the file, the other methods, is the file from the is the path from the current file. Yeah. So it's the current one, and then joins with data. So it's this one, maybe. And the thing is that this is inside of the loader, so, but I assume it's this directory here. So just getting the directory of the data. And then is getting from each kind. Node, real, simple, PyTorch converted, PyTorch operator. So that's why it's calling multiple different ones. The thing is, I can't look at the source code to understand what the tests are about, and I think the documentation doesn't explain there. I want to understand how is it testing the models? Because obviously the only way that I'm gonna be able to see if I can fix some of these mistakes is if I understand what the model is trying to test for. Also don't understand, like, where is this coming from? PyTorch converted. So it's probably coming from this thing here. Yes, reflections. Yeah, there we go. But it is just reflection there. So I think it's just running all the tests for these files. So let me think about what other thing that I wanna clarify in my mind. It's passing this to this thing here. So the backend is gonna be the class, which is this one, which inherits the backend. Module itself backend. Then it's gonna run this stuff, which is gonna load all the tasks, I think. Kinder than task name. This is gonna be all the tasks inside of the data. So some of them have model tasks, Some of them don't. Then appends everything to this thing as cases. So this returns a giant list and then it loops over them. So it's pretty much getting all the files inside of those directories and creates this thing, which is just going to be a simple class. I think that it is a data class that gets all the information for each one. I think I remember looking into this. Is there artol? It's probably tolerance, some sort of tolerance. Probably the tolerance for accuracy. Blah blah blah. Context of machine learning artol and atol refer to the relative and absolute tolerances respectively. Determine convergence or closeness of numerical computations or comparisons. Often used in various numerical optimizations, blah blah blah. Okay, so it appends everything to this, and then it's gonna call this function, which is gonna add the tasks to this dictionary here, probably. I think it's passing the task, which is the name of the file, inside of here, and the kind of tasks. So the name and the kind. And it's gonna pass this stuff to the function. Kind plus model. Not task, not name. Yeah, so it is a class that has the information for each task. So it's gonna be the other class. Let me go back. It's gonna have this information here. Name, model name, URL. Maybe I should look into the other function first. This one. So this stuff creates the key value pair on these test items. So category device test name. Category is the kind plus the model. And this is just gonna run. But I don't understand how does it run the task. It's just passing. Maybe it runs at the point that it creates the class there. Or it has to be here actually. Yeah, maybe at this point it calls. So one easy way to test is just to delete this. Let's, yeah. So I think the first functions that it has there, it just, like when it initializes the class, it just passes everything into the dictionary there. I think that's how it works. I think I understand now how it works. Then when it updates the global scope with this function call here. And then this is the thing that makes the task run, maybe. It's calling that, and then task cases. So this is gonna return the self, which is the class. And the task cases is gonna be a list of all the tasks. So maybe it doesn't run at this point, it just creates the task at this point on the task cases. And then when it runs the updates, it runs all the files one by one. It's just running all the tasks from the files inside of the backend, but like now I have to understand more how does what is it testing for? The onnx. Yeah, let me think about it. Yeah, that's the thing. The issue is I can't really see the source code. That's the problem. It's gonna get wrong stuff. Task items. So it filters the tasks based on the ones that it excluded there. And then it runs all the files, I think. Let's have these updates here. I want to understand what is the point of passing this class, though. Like what is the point of these functions here? So this one returns the other one. Like from reading, I think I understand. It's just preparing it's a function to prepare the model to tasks with the onnx backend. But I don't understand really well the nuances of it, I think. Just the inputs and the device. Maybe it's this function here. I have to see what this function does. And also have to see this class here. Understand what the classes do. I'm gonna study these two different classes here to understand how they work. Then I think after that, the thing is I don't really know because I'm probably not gonna be able to do anything. Yeah, I'm not gonna have enough time to try to do a bounty. I think it's just too much to like try to do it in a day. Learn everything and do it in a day. Maybe I can divide Because the thing I don't wanna is I don't wanna lose track of the stuff that I'm doing with React there. Like I need to solve that problem before I dive deeper into this thing. And the React problem is really annoying to solve. I'm gonna have to spend, like, who knows how much time I'm gonna have to spend more to try to solve that one. But I wanna get to this point. So maybe I can compromise on the solution on the React stuff and just like do a simple, because I think I can come up with different solutions for that one, but like the way to solve that one is just to change the logic when the component mounts, and that's gonna, or to change the logic on the reconciler, maybe that works as well, and that's gonna make it so that it mounts the components that depend on the context first. So I think I can do that, but that's not the best solution, because to get the best solution I have to understand how the update container is working, why isn't mounting the components. So that's gonna take a lot of time, that's the problem. But I wanna get over with that fast. It's kind of annoying me. That's one of the reasons why I decided to study this stuff here now. It's just taking too much time, and I'm tired of studying the same stuff, because React is really confusing. It's not, I don't think that it's hard to understand. The problem is just that it's a lot of different functions. Is the whole point of the thing that I'm trying to do is like, it's very annoying to go back and forth and to step through, and it's just a waste of time. So it would be easier, a lot easier, if I could visualize everything. So like maybe when I get to the point that I'm gonna work on the abstract syntax tree and the other stuff to actually create a visualization, to think about how, which is the part that I'm most interested about now, is how I'm gonna design this stuff that it gets, the parses the files and gets what's most valuable out of them to put on a graph visualization. That's the stuff that and how to structure the graph, obviously. This is another difficult thing, because it's gonna depend on the data structure. And I wanna get to the point, because then I think I can, the great thing about doing what I'm gonna do is that I can use the stuff that I build to learn all of this other stuff, and then by doing that I'm gonna be able to improve it a lot. So like, you kill two birds with one stone. Like I could be working on that now, and then as I create the graph, I can use the graph to study, and it's gonna make it easier to understand how like this stuff works. So that's what is making me think that it's probably better to just stop here. I think I'm gonna study this. I think I'm gonna watch videos now. I'm gonna watch videos and I'm gonna study these two classes here to try to understand, and then I'll go back to doing the React stuff. Then I finish the React, and then once I finish the React and I have like everything set up to create the visualizations, I fix the custom renderer, and then I add the ability to customize the graph. I think that those are the main things that I have to do before. Once I get to that point, then I go back to this stuff, and then as I build something that parses the files, I'm gonna be able to simultaneously study this, because I can use the stuff that I'm building to see if I can make it easier to understand what is going on here. It's not that difficult to understand, I think, how this stuff works. The main difficult thing is, I think, is understanding how the tasks work. That's gonna be annoying to do, because I can't look at the source codes. It might be a better approach just study the models, the source code of tinygrad first, and then try to modify, like, play around with modifying a bunch to see how it's gonna change the tasks. Maybe I can run other files for other tasks as well that are more simple. And then by doing that and changing a bunch of times, I'm gonna be able to understand how it works. I think I have a decent intuitive understanding, but very far from understanding exactly how everything works and is connected. I think if I spend some time reading the source code, it's gonna be easy to understand how it works. Because it's not that he spent a lot of time like simplifying everything, I think, and making it better, so now it should be a lot easier to understand. I assume that the tasks are calling these functions, probably. And these functions prepares the inputs to test the library or the models from the library. And then tensors create the stuff that you're gonna use to do the calculations, obviously. So it might be better to like play around with this, try to build stuff with tinygrad directly, and then because that's gonna help me understand how everything is structured, how the model works, and also study the other models as well, the NVIDIA ones from MLPerf. And then once I do that, then it's gonna be easier to understand what the tests are testing for. And I think he explains as well that he made stuff to be lazily loaded, which means that he's not going to do the computation until it's necessary to do it. I think it just creates the structure first, and then when it gets time to compute, it does the computation. And then there's some trade-offs with that I don't understand really well. So maybe these functions are used because the backend of onnx is gonna pass the model and the device to this stuff to prepare the models for testing, I think. So it gets the inputs and the initializer, which maybe has to do with the data, not really sure. I guess I can search for this stuff as well. And then it's gonna pass this to this stuff, and then this is gonna get the weights and biases that it creates, and that it creates this stuff based on the tinygrad thing, which is the tensor, and the tensor is the stuff that is gonna create the weights and biases, because it's pretty much matrix multiplication that creates the equations and separates based on the data type here. It returns this. This should have all these functions here. Okay. So loops over the initializers and call this the other functions now. And returns this function. So this is the function probably that. The other thing that I want to understand is how does it make it so that he can pass like graph variables here. I saw him do it on the stream where he does stuff like this and then he calls Python. I don't understand how that works. And it's very hard to think about how to search for this. And I think he's using tmux, however you say that. Maybe there's something about this, but and I think it has to do with this get environment variables, but not really sure about it. So I think that's probably what all these tests are about, is this function here. I'm not really sure. Yeah, the main thing that I'm lacking here is it's probably about everything actually, because this function is gonna call a bunch of different other functions. So it probably tasks for stuff on the tensor and on this function here. So, but the main thing that I lack is understanding how, like, what exactly is the tests are going to be testing for. I assume they're going to call these functions, the classes from onnx, and that's what is going to be tested. What does RAT stands for? I'm gonna copy this stuff and I'm gonna put on ChatGPT. So backend is the framework that is going to run the model. So you can have several different ones, like I think PyTorch, TensorFlow, the ones that I know. And I think there are a lot of other ones. So I think I'm starting to understand how it works. And then tinygrad is a library to run them, run the models, and then those stats are gonna task the onnx with the tinygrad backend. So it's testing the tensors from tinygrad to run the onnx models. I think that's what it's doing. And probably the tensors are the core of the library, the tinygrad library. I think studying PyTorch probably would help as well, because I think I studied TensorFlow more, but to understand what is the essence of these libraries, because I think what he's trying to do is pretty much similar. And there also he talks about some stuff related to the hardware, which I don't understand really well, that I think he's planning to use this for Coma AI. Like once he gets good enough, he's gonna do some stuff with Coma to do specialized hardware to make the stuff faster. And I think that's what the other companies are doing with NVIDIA and Google are doing, using their custom hardware to use these libraries to create or run models. So, but I don't understand really well how it works. I was watching these videos, but the thing about these videos, I'm not really sure if I'm gonna watch the videos. Maybe I'll just go like start working on the React stuff right now. Because I was watching these videos and it's very, like, it's not for me. Obviously it's very good because it's free and there's a lot of information. So obviously I'm not complaining, but it's not for my style, I think. It's just true, it reminds me too much of college, which is just a waste of time for the most part. Like, it doesn't, like, I want stuff to get as straight to the point as possible. Like, skip all the bullshit. And I think because of the nature of the videos, it's just usually going to be for a broader audience. So there's going to be a bunch of stuff that doesn't matter. So that's why I've, like, more and more, like, the more experience I get, the more I start to think like this. I think I'm still having the tendency of watching videos because that's how I learn for the most part. But I think I'm already at the stage where it's probably a lot better, more efficient to just go straight for the source code and then just spend time like studying the source code directly instead of trying to watch all these videos. But the good thing about videos is that it's very low effort though, so a combination of both is probably the best. Because studying the source code is yeah, I'm not sure how to say it. Like, it can be, it's like more draining. It requires more energy, I think. It's more boring, let's say. The videos is easier to watch. But then usually I end up having to put at 3x speed or something like that, and then it gets very difficult to understand what they're saying, because I just want to skip all this stuff that doesn't matter. Yeah, but I think I'm starting to understand how everything works on this stuff. The question is how... Yeah, the thing is that I have to study a lot more the onnx library. Also understand the other models like PyTorch, how to do it, how to do the model with PyTorch. I think micrograd, however you say that. Someone shared here. Maybe I should look into that first as well. Yeah, go build Andrew's micrograd. Because that's gonna give me some context to... Yeah, because first I have to see one version that is already working the way that he's trying to make it, I think. I think the bounties is to make the same models work with a different backend, which is the backend from tinygrad. So first I have to understand more how the other one works. So that way it's gonna be easier to understand what is... Like what are the testing for. But it's gonna take a lot of time, I think. It's probably better to just go back to working with the React stuff. And then I'll continue to do... I'll focus on this once I have the rendering fixed and I build some stuff for allowing for customizing the visualization. And I have to spend some time studying the Pixie library as well. But I think it's probably a better idea to just go right away. Like once I do simple visualization, simple customizations on Pixie. And the thing is I have to implement the event listeners as well, which is gonna be a pain in the ass, I think, as well. But I think it would be probably better to try to get as fast as possible to the point I'm actually building the stuff that is gonna matter, which is the how to translate the code into graph, and how to capture the data flow and things like that. Like to figure out how to capture as much information as possible from code to try to understand it better. Because once I do that, then I can use that to study all this other stuff, which I think is going to be really interesting to do. So it makes more sense to do that first, I think, because then I can use it and then I can study this stuff using that. And then I'm going to improve on both simultaneously if I do it like that. Oh, there's a video. There's also a playlist from this guy as well. He teaches a bunch of stuff. I think I might watch some of these videos. Yeah, but I think I'm gonna stop here. Probably tomorrow I'm gonna go back to trying to fix the stuff on React. I'm gonna step through the source code and see if I can fix the rendering thing. Then once I get to the point, I go back and I try to use the stuff that I built to continue to study this stuff here. But I'm gonna watch these videos off stream as well. And maybe study a little bit of the source code as well. So yeah, probably gonna come back tomorrow and continue to do the React stuff. So